Hello calculus students, here we are with the fundamental theorem of calculus, where we're going to evaluate definite integrals using this fundamental theorem, and use the mean value theorem for integrals, and also find the average value of a function over a closed interval. We will not be doing the second fundamental theorem of calculus, which comes up later in the chapter. So here we go, the fundamental theorem of calculus. This actually came up from two gentlemen way back when. Both Newton and Leibniz discovered it independently at about the same time. And basically it's just saying that differentiation and integration are inverse operations. We can see that with this diagram here, that we've spent a lot of time changing the slope of a secant line, which used our traditional y2 minus y1 over x2 minus x1 formula, and let that delta x go to 0 so that we could get the slope of the tangent line, and that's called differentiation. See how the secant line turns into a tangent line. Now similarly, we're going to take the area of a rectangle and use a bunch of little rectangles to come up with the area of a region under the curve. And that's definite integration that we just looked at. So here's the fundamental theorem of calculus. That if f is continuous on the closed interval from a to b, and f is the antiderivative of little f on the interval from a to b, then the integral from a to b of fx dx equals f of b minus f of a. Now remember, big F is the antiderivative of little f. And so here's the example of how you use the fundamental theorem of calculus. Provided you can find an antiderivative of f, you can use this. And so we use this strange notation here with this bracket. See this up here? That if we integrate from a to b and find the area under the curve of f of x between x equals a and x equals b, that we're actually going to put b and a into the antiderivative function and it work out like that. For instance, to do the integral from 1 to 3 of x cubed dx, we do the antiderivative of x cubed, which is x to the 4th over 4, and then evaluate it from 1 to 3. So that means put the 3 in for x, put the 1 in for x, and look at the difference, and that'll tell you the definite integral. Now notice we don't have to use a constant integration when we're doing this antiderivative because it would just show up in each of both f of a and f of b and it would just cancel out. So that's why we can just jump right to that. Detailed proof is in your book. We're going to focus on the applications here. And let's try this first definite integral here. Integral from 1 to 2 of x cubed minus 3 over 2. Visually what we're trying to do is come up with the area under the curve of x squared minus 3. So it's going to have a happy parabola like that from 1 to 2. And so we're going to get a little of the area above and a little area below there, and I think we're going to get more below. So we might end up with something negative here. So first we take the antiderivative of what's inside here. We crank up the power, x cubed over 3 minus 3x, and we evaluate that from 1 to 2. That's what we mean by the antiderivative. So in this case, f of x was x squared minus 3, but the antiderivative big F of x is x cubed over 3 minus 3x plus some constant. So we put 2 in, 2 cubed over 3 minus 3 times 2, and then we subtract from that what we get when we put 1 in. 1 cubed over 3 minus 3 times 1. That's how you evaluate the antiderivative. Let's see what this works out to be. So that's 8 thirds minus 6 minus a third. Minus and minus makes plus 3. So I'm getting 7 thirds minus 3. And minus 3 is 9 thirds. So we get negative 2 thirds. Negative 2 thirds. And we can check this on the T89. And let me show you I can do the check. Here's the TI-89 check. First we go back to what we had before. Look at the original problem there. Gonna pin that down. And then here's the TI-89 check. You use the integral symbol, which is right there above the 7. and you put in the function inside, x raised to the 2 minus 3, comma, and then specify what what variable you're taking the integral with respect to, and that's x, and then put the limits of integration in 1 to 2. So very straightforward. So let's give it a try now on your calculator. Integral symbol, x raised to the 2 minus 3, comma, x, comma, 1, comma, 2. And I get negative 2/3. Negative 2/3. And we see I made my first mistake. Oh no, that's what we came up with, right? Yeah. Take off that. Negative 2/3. Kabinga. All right, let's try another one. Integral from 1 to 4, and there's a definite integral of 3 squared of x. So you can see at 1, you're going to have 3, and at 4, it's going to be up to 6. And you get a curve like that, and you're looking for the area under the curve. So this definitely looks like it's going to be positive. Some of your homework is just to figure out if the area mentioned is going to be positive or negative. You can do that with a sketch. So be careful. Don't put the 1 and 4 into this. We have to do the antiderivative of 3 squared of x. And remember, this is x to the 1/2. So it's going to be 3x to the 3/2 divided by 3/2 evaluated from 1 to 4. So I'm going to simplify this a little bit here. The 3's cancel, and we get 2x to the 3/2 from 1 to 4. So we put 4 in. 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. 4 to the 1/2 is 2 squared, so 16 minus 2, I'm getting 14. Let's see what the 89 says. Integral symbol of parentheses 3 square root x, comma, x going from 1 to 4. And let's see what that comes up with. Integral symbol 3 square root x, comma, x going from 1 to 4, and parentheses, get 14. Oh, joy. Now, let's do a definite integral involving absolute value. Integral from 0 to 2 of absolute value 2x minus 1 dx. Well, here's what it looks like. 2x minus 1 is this little break at 1/2. Because that's what makes this whole thing equal to 0. So anything to the right of 1/2, we ignore the absolute values because the thing inside is positive. So on this side, you're basically getting y equals 2x minus 1. Over here, you're getting y equals the opposite of 2x minus 1, or negative 2x plus 1. So it's a tricky one to integrate, and what you have to do is split it up. So here's our plan. We're going to take the integral from 0 to 1/2 of absolute value of 2x minus 1 dx, plus the integral from 1/2 to 2 of absolute value of 2x minus 1 dx. And see, in this region, 2x minus 1 is positive. When x is greater than 1/2, 2x minus 1 is greater than 0. So we can just call this 1/2 to 2 of 2x minus 1 dx. On this side, when x is less than 1/2, 2x minus 1 is going to be less than 0. So this becomes the opposite of 2x minus 1 dx. So we have slightly different things to take the antiderivative of. So this negative can come on outside here. The integral from 0 to 1/2 of 2x minus 1 dx, plus the integral from 1/2 to 2 of 2x minus 1 dx. And we crank both up. So 2x becomes x squared, minus 1 becomes minus x, and we're going to evaluate that from 0 to 1/2. And don't forget, though, that we had this negative sign out here. Plus, the antiderivative of 2x is x squared minus x, and we're going to evaluate all that from 1/2 to 2. So put the top number in first. So it's 1/2 squared minus 1/2. All of that minus, put in 0, and you just get 0. Now this one's going to be a little trickier. We've got to put 2 in, 2 squared minus 2, and then put 1/2 in. 1/2 squared minus 1/2. But all that gets subtracted. Oh, Neller. So we have the opposite of 1/4 minus 1/2. So that's negative 1/4. So that's 1/4. And over here you get 2 squared 4 minus 2 is 2 plus A half squared is a fourth minus a half. But remember, this is the opposite, adding the opposite of. So we get a fourth plus 2 plus, this is negative a fourth, but it's negative that, so it's a fourth. So I'm getting 2 and 2/4, or 2 and a half. Okay, cross your fingers. Let's see what the TI-89 says. Integral of absolute value of 2x minus 1 from 0 to 2. So you put in ABS, 2x minus 1, x going from 0 to 2. Let's see how we did. Integral is above the 7 of the absolute value. That's the first thing in the catalog. So you just go to catalog and hit the A. I'll get you right up there. ABS. 2x minus 1, comma, x going from 0 to 2. And we get 5 halves. Check, please. There we go. Now, using the fundamental theorem to find area. Find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2. The x-axis and the vertical lines x equals 0 and x equals 2 as shown in this figure. Okay. So there's part of the parabola going from 0 to 2, and we want the area bounded by all these things. So it's the integral from 0 to 2 of 2x squared minus 3x plus 2 dx. Remember, this dx is important because that's what you're doing with the area under the curve. You're multiplying the y values times little changes in x to come up with a bunch of tiny little rectangles. And add them all up to come up with the area. So we do the antiderivative. So this is 2 times x cubed over 3 minus 3 times x squared over 2 plus 2x evaluated from 0 to 2. So let's put the 2 in. We get 2 times 2 cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2. That's all just putting in x equals 2. Now you got to put in x equals 0, but I think you can see it's just going to be 0 minus 0 plus 0. So that's nice that they gave us a 0 on that one. So we get 16 thirds minus 12 plus 4 minus 0. So that's 16 thirds minus 8, which is 16 thirds minus 24 thirds. Yep, which is minus 8 thirds. And we're wrong. Let's find our mistake. It says here is 10 thirds. So I think it's a matter of I did not multiply enough here somewhere. Let's look around. Minus 3 plus 2x. Put in 2. We got a 4 there. Minus 8, 16 thirds. Why is this coming up negative? 2x cubed over 3. That's all good. 2 is 2x. We put the 2 in. 2 cubed is 8 times 2 is 16. That should be 16 thirds. No. God, what is that? We put the 2 in here. Oh, this is minus 6. So sorry. 2 squared is 4 divided by 2 is 2. That's 6. So, see how we found a mistake by carefully going back and figuring it out. So here we go. This was 6. So it ends up being minus 2. So that's 16 thirds minus 6 thirds is 10 thirds. And that checks with the answer. Okay, now the mean value theorem for integrals. If f is continuous on a closed interval, and there exists a number c in the closed interval such that the integral from a to b of fx dx equals f of c times b minus a, that basically you can come up with sort of an average value for all these possibilities by changing this strange shape into a rectangle. Well, the area underneath this strange shape, that is the integral. So the integral here equals this strange area like this. And what this equals is the rectangle That's f of c high and b minus a long, because that's the gap here from a to b, b minus a. So that's the idea behind the mean value theorem. And there's the mean value rectangle. And the average value is the thing guaranteed by this theorem. So if I divide both sides by b minus a, I can come up with what this average value f of c is here. F of c equals the average value. And it's a way of kind of averaging out a very strange looking function where you can't just add up a bunch of numbers, divide by n, but you've got this continuous function. So if f is integrable on the closed interval, then the average value is defined as 1 over b minus a times the integral from a to b of f of x dx. So that's the average value. It's a little like taking an ice sculpture like this, melting it down, and then refreezing it. So the height of this would be your average value. Would be the height of this new block of ice. Even though we're much taller here, much shorter in some things if you melt it all down. So find the average value of this function, 3x squared minus 2x on this interval from 1 to 4. And we've got the answer there already. But let's see how you go about that answer. To find the average value, it will be 1 over b minus a times the integral from a to b of f of x dx. So 1 over 4 minus 1, integral from 1 to 4 of 3x squared minus 2x dx. So 1/3 integral from 1 to 4 of 3x squared minus 2x dx. Alright, so that's 1/3, and now we crank this up a power. We say 3x cubed over 3 minus 2x squared over 2 evaluated from 1 to 4. Now that simplifies a bit. We get x cubed minus x squared evaluated from 1 to 4. So it's 1/3 4 cubed minus 4 squared minus 1 cubed minus 1 squared. So that's 1/3 64 minus 16 minus 0, and that looks like 48, 1/3 of 48, which I believe is 16, and that checks out with the average value. Okay, flange out.